Hello everyone, and welcome to this course on electromagnetic interference and electromagnetic compatibility. This is the second video out of a set of 3 videos. My name is Abhijit, and I'll be talking in this video about some case studies. In the previous video, we have talked about an introduction to EMI, EMC, some motivation and why these concepts are important, and we have done some coverage of the background about EMI and EMC. In this video, we are going to take one circuit at a time and analyze EMI issues that may come about in each of them. The circuits are inspired by real circuits and real applications, although they are a little simplified, but they are not contrived examples, so they are fairly real world examples. So let's get started. Let's look at the first circuit here. This is a linear supply for a heater coil. I'll just give a brief background about what the circuit is and what's going on. So the application is, say, a process industry where you have a tank which contains some chemicals that need to be maintained at a fixed temperature. And to do that, we have a heater coil, which is just a resistive element, which is going to carry current and heat up and therefore keep the tank temperature at the desired value. Now, what is going to happen is that controlling the current in this heater coil is going to affect the temperature of this tank. And of course, there's going to be some feedback mechanism where there'll be a temperature sensor measuring the temperature here and feeding it back to give us the desired current that needs to be fed. Now, we've simplified this a little bit, and what we are doing here is that this is like some microcontroller or a controller which basically outputs some analog value, and that analog value is converted to the current by this op amp and this power transistor here. So now let's see what's going to happen. This heater coil is going to take a fairly large amount of current because we need to dissipate a large amount of energy, and that large current cannot be supplied by the op amp, which is why we have put a power transistor here. This heater can operate either in the linear mode, which means that the current through this heater coil can vary between 0 and the maximum. And in the extreme case, it may even operate in the on-off mode, which means that when you want to heat the tank, the current may go from 0 up to the maximum value. And if you want to quickly cool the tank, the current may go from the present value back to 0. So this is the circuit. Now let's look at what's going to happen. Here we assume that the heater resistance doesn't change much as a function of the temperature, which is just a simplification we are doing. And we are assuming that this is just an open loop microcontroller based control system. So now let's see what's going to happen. First of all, we know that conductors are not ideal, which means that the wires that carry the current to the heater are going to have some amount of resistance, and they're going to have some amount of inductance or reactance. Now, what's going to happen when this large heater current flows through these wires? Here we assume that the real circuit was wired up exactly as shown in this schematic circuit diagram. Now, as I mentioned, the power lines, which means the conductors carrying this high power current, they have inductance and resistance. Now, let's look at this particular node. Based on the control variable or the amount of power that needs to be delivered, the microcontroller is going to set the voltage at this node, which is basically the non-inverting input of this op amp. Now, based on that voltage, the op amp is going to control the output voltage such that this node here matches the non-inverting input. Basically, the op amp ensures that the inverting and non-inverting inputs are at the same voltage. Unfortunately, supposing we were to increase this node by a slight amount, which means we want to increase the current in the heater coil by a small amount. As a result of that, the voltage at this node will increase. When this voltage increases, this is the base voltage of this transistor, and what is going to happen is that this transistor begins to conduct better and drives a larger current down the emitter, through the collector and out of the emitter. As a result, because the current through this path has increased, the voltage drop across this parasitic impedance has also increased. As a result of which, the voltage at this node is going to drop. That is because the voltage at this node is equal to the voltage here minus the drop across all these parasitic impedances. So the heavier the current we draw through this line, the more is going to be the voltage drop here. Now what is going to happen is that as the voltage to this power supply drops, basically the power pins of the op-amp effectively see a reduction in the supply voltage. Because the supply voltage goes down, the output voltage also goes down. Noise or disturbance on the power rails can cause a disturbance on the output rail. However, the important thing to note here is that because these are not purely resistive, they are partially inductive as well, these elements. There is a certain time lag between the change in current here, or rather the change in voltage, which causes a change in current, which causes a change in voltage here, and which can then feed back to cause a change in voltage here. So what we see in this loop, what has happened is that a slight change in voltage here, a slight increase here, has caused a slight decrease a little bit later. Now what happens when this voltage decreases? When this voltage decreases, the base voltage of the transistor will also decrease, and when the base voltage decreases, the current through this emitter or the collector is also going to decrease, as a result of which, with the total current drawn through the supply decreases, and this voltage will go back up. When this voltage goes back up, we see a base voltage increase again, and this cycle continues forever. This basically is a parasitic oscillator that has formed, and this can cause severe oscillation in the output depending on the circuit parameters. This is a known problem in many audio amplifiers. Under certain conditions, it could cause the output to start making a loud noise, much like a motorboat, and it used to be called motorboating. So let's see what is the solution to this. This is, of course, what we need to eliminate. We need to eliminate the effect of an increase in voltage at the input and eliminate that link through the power supply. So first thing we are going to do is eliminate the shared current path, which is what was causing the problem. So instead of wiring the op-amp supply rails to the shared node or the shared current path, we'll use separate conductors or separate wire and wire it directly to the battery. Now in this case, the high power current or the large current that was flowing through the heater flows through a different conductor, and because that current does not flow or does not have a shared conduction path with the op-amp supply rail, there is no effect of the current on the output voltage here. So that is the first solution to eliminate that problem. As you can recall, this effect is called conducted noise. Basically, change in the current here, change in current drawn by the load, was causing a change in voltage here, which was due to shared conduction path. The next thing we need to look at is the loop area. As you can see, the high current that is being drawn by the heater is taking this path shown by the dotted line here. Now we know that this current is going to be large, and it may have some switching component as well. Supposing we want to turn on or turn off the heater quickly, a large current is going to flow through this path. Now what is the area associated with this loop? That is fairly large, and if the heater coil were to turn on or turn off suddenly, we expect that a large amount of electromagnetic energy will be radiated. This can especially be a big problem if the heater coil is far away from the control system. So To reduce that problem, what we can do is reduce the area associated with this loop. Now, how do we do that? We basically run the conductors as close to each other as possible. So this is an example of how that can be done. We basically use two conductors that run very close to each other, and in this case the effective area is greatly reduced. The next thing to do is that in addition to separating the power supply leads of the op-amp from the high current path, we can also add a little bit of capacitance to the power supply nodes. This is called power supply decoupling, and this basically ensures that any noise or any change in the voltage here is suppressed and does not affect the op-amp supply voltage. So we have taken 3 steps in this very simple circuit to eliminate some potential EMI and EMC problems. So to summarize, first, we have eliminated the shared current path. We have done that by wiring the heater coil directly to the power source or the battery and not allowing any of that current to flow through the leads that also carry power to the op-amp or to the control system. The second thing we did is we reduced the loop area. This reduction in loop area is done simply by running the power leads as close to each other as possible, and typically we can use cables that have multiple conductors in the same housing, or we can physically bind the conductors together depending on the application, of course. And by doing this, we reduce the area associated with this loop and therefore reduce or eliminate the amount of EM radiation or electromagnetic energy that will be radiated by this loop. The third thing that we did was to stiffen the op-amp power supply rail, which means we added a capacitance here, and this capacitance ensures that any noise in the power supply rail does not reach the op-amp supply. Next, we are going to look at a flyback converter. I assume that you are all familiar with the working of a flyback converter, and the EMI and EMC issues for this converter are going to be related to the fact that this is a switching converter and also has high dV by dt, which means the voltage at some of these nodes changes quite rapidly. In this case, we are going to take a quick look at how layout for such a converter is critical. So let's say we have some rules about the layout. We need to lay it out on a single-sided board and using only through-hole components, which means no SMD components. So here is a quick layout done by somebody who's probably not very familiar with EMI and EMC constraints. And going by the electrical circuit wise, this layout is fine, it's going to work. But let's look at what are the problems that can come about as a result of this layout. First of all, let's look at the high current path in both the circuit and correspondingly in the layout. So we see that the switching current is going to have the path as highlighted in red, and on the layout that has actually a fairly large area, and this large area can have a couple of problems. The first is that switching current is going to lead to radiated noise, which means this loop will emit EM radiation. The second thing is that these traces are non-ideal, they have impedance, and that can create ground bounce issue, which is conducted noise, which is what we saw in the previous example. So let's see what we can do to improve this layout. The first thing is we want to reduce the area, so we want to tighten up the layout a little bit. Simply by moving the components, we are able to achieve that, and you can see that I've changed the layout a little bit now using the same components, the same footprints, but just changing their positioning in order to virtually eliminate the high current loop area. And it is important to note in this case that not only is the primary side important, but the secondary side as well, because both sides are going to have switching currents. Just a side note here is that most of the switching current will come through this capacitance, and what we saw in the previous example was that the capacitance has to have a very low impedance for these high frequency currents. So typically designers will select a capacitance with very low equivalent series impedance, that is the ESR and ESL in such applications. Now let's look at what's going to happen to the op amp in our circuit, which is just representative of other circuits that may be next to the switching power supply. So earlier we saw that the current was flowing through this conducted, through this trace, and like in the previous example, this is going to cause a ground bounce at this node, which means that the power supply for this op amp is going to change and can result in noise coming at the output. In the improved circuit, in the improved layout, what we've done is we've eliminated the shared current path, and the op amp supply now does not share any trace with the high current path. So you eliminate that problem as well, and that eliminates ground noise or conducted noise from reaching the op amp. Now let's look at what is called differential mode noise. Consider the flyback switching part of the flyback converter. Let's say it's connected to a DC source which is slightly far away. It could be a battery or it could be just a wall mounted power supply. And the current that is drawn by this flyback converter has a triangular shape, as we know. So it's going to draw this triangular shaped current when the switch is on, and this dotted line shows the current that freewheels through the secondary when this main FET turns off. So we are concerned more with the primary side current to begin with. Now most of this current, as we know, is going to come from this capacitance, and as we also know, this capacitance has some impedance which is called the equivalent series impedance. This is the ESR and the ESL, equivalent series resistance, equivalent series impedance or inductance. And the lines that connect this power supply VCC are also not ideal, so they are going to have some impedance as well. Based on the two impedances, most of the current is going to come from this capacitor, because we expect that this impedance is going to be really low, but some current can still come directly from the power supply. Of course, we are talking about high frequency currents here. If there was some other system also connected across these nodes here, then the voltage seen by this piece of equipment is going to be the VCC minus the drop across the series impedance. And the drop across this series impedance is dependent on how much current is drawn by this. So in this case, the ratio of impedances, these two, is going to determine how much noise is seen by this victim. Now let's look at some issues with the heatsink. Now we know that in a sizable power electronic converter, the switch dissipates a fair amount of energy. So what's going to happen to the VDS at this drain node? So that's fairly simple. We know that when the switch is on, VDS is 0. When the switch turns off, the inductance freewheels through the secondary side like this, and the output voltage is VCC plus VO. And depending on whether or not we are in DCM, we may also have a third state here, which is VCC. And each of these transitions is going to have a very high dV by dt. And depending on how fast we are switching this, what device it is, that will determine how fast these edges are. And so basically VDS is going to be trapezoidal, and the fundamental frequency is going to be the same as the switching frequency of this converter. And all of these are high dV by dt transitions. So now let's look at how this VDS is going to cause EMI problems. We know that this FET or power semiconductor switch is going to need a heatsink, and in most semiconductor switches, the drain of the MOSFET or the collector in case of BJTs is connected to the heatsink tab to be able to dissipate heat in the most effective way. If we don't do anything and we just leave this transistor freestanding, then this is going to act like a stub antenna, which we discussed earlier, and whichever higher harmonic matches the stub wavelength, that frequency will radiate, and basically we may fail the radiated emission test. Supposing we add a large heatsink, that heatsink just becomes a bigger antenna, and sometimes the fins on the heatsink can improve or change the directionality of that antenna as well. So that's not such a good idea. As I mentioned, the tab case or heatsink often has a large area by design because it has to dissipate a lot of energy and forms one parallel plate of a capacitance. Because this voltage is switching, this large area can couple noise into other parts of the circuit as well. So this is the second problem with VDS having a switching voltage. So we can have noise induced in other nearby parts of the circuit just by having switching voltage at the drain. Now, one solution is to simply ground the heatsink, but often it can't be done. One of the reasons is that the heatsink can't have high voltages, so we can't have it exposed. And many times the heatsink is connected to multiple devices, and as a result, we cannot ground the heatsink directly. And in some cases, the equipment body acts as the heatsink. So we need some electrical insulation between the case and the heatsink. So what do we do? Typically, we add some mica, and what is going to happen as a result is that it's going to form a parasitic capacitance between the actual heatsink and the power device. Now, if we leave this heatsink floating, we can still get some amount of coupling based on the parasitic capacitance here and the parasitic capacitance here. There's still going to be some noise that couples into our nearby circuits. So to analyze this situation, what we can do is we can model this entire system as a switching noise voltage connected to the drain and how that affects the system. So we saw that we can't leave this floating. So where can we connect? One way is we can connect it directly to the return. Now, basically this is the ideal solution, and it shorts out this parasitic capacitance that is formed, and now no more energy will couple into the victim. So we've solved the problem. However, this is not possible if this heatsink is exposed and has to be grounded, or it is connected to the chassis of the system and so on. What happens if we were to ground this heatsink? Which means we connect this heatsink to the earth of the equipment. Now, what does the circuit look like for the high frequency voltage at this drain? So let's do the modeling, and this is what it looks like. This inductor is basically an open or high impedance for high frequency. This capacitor is effectively a short, and these line and neutral lines are connected to the VCC and ground through a rectifier, and at any time two of these diodes are always conducting. So let's just look at an instance where these two diodes are conducting. So the high frequency current is going to have this path that is highlighted in the circuit diagram. Basically it flows all the way out, and wherever there is coupling, capacitive coupling between the live and neutral wires and the earth, the current will circulate like this. In fact, this earth is often tied directly to the neutral at the far end, so the current can flow all the way out and then come back. Now what's the problem here? The problem is that this large loop can set up EM fields, and this can radiate. And the other thing is that current flowing through this line constitutes conducted emission, which is not allowed and which is limited by the EMI standards. So we need to reduce that. Now let's just quickly contrast common mode and differential mode paths. So we saw that this current can take one of two paths. It can flow either through either the live wire or the neutral wire. And this is why it is called common mode current, because it is common to both lines. In contrast, the differential mode current that we saw in the previous analysis of the flyback converter flows in through the line and then back through the neutral. So again, just to recap, what is the problem with common mode? One is that we will fail radiated and conducted noise limits, and we'll fail compliance testing. So what is the solution for common mode noise? If you were to add the filter like we did earlier, this is not going to solve the problem entirely, because common mode noise can bypass or has a bypass path through the other power line. So this is not going to help much. Inductance on one power line does not affect common mode noise. So what we can do is we can add this inductance in a split form. We can add it to both of the power lines, and this should affect common mode as well as differential mode noise. The net impedance seen by the common mode is the parallel combination of impedance on these two lines. Now what if we want to eliminate common mode current altogether? You see, typically we have some constraints. One of them is that the heatsink must be grounded. We don't want any current through the ground line, and we also want to eliminate radiated and conducted noise. So in this case, the easiest solution to that is to add a copper shield between the case and the heatsink. And this copper shield is just a thin layer of conducting material, usually copper, and that is placed between the case of the semiconductor device or the heatsink tab and the actual heatsink, and the heatsink can be grounded. Now let's look at the equivalent circuit model for this. We have now formed two parasitic capacitances. The noise source, which was the VDS switching voltage, is now shorted out by this shield strap or the shield foil, and we have eliminated the problem of switching noise. This is an example of how this might be implemented. We have the transistor here, we have an insulating material which is a sill pad, and we have a copper shield which is connected to the negative terminal, and we have a grounded heatsink which is connected. So all these are thermally conductive, but only the copper is an electrical conductor. A similar situation is seen due to inter and intra-winding capacitances in the flyback transformer. Since the primary and secondary windings are in close proximity, a large capacitance can develop between these two windings. This is a parasitic capacitance. This parasitic capacitance can be modeled as two physical bulk capacitors, and they are shown in the figure below. Remember that these are actually distributed capacitance, but for the purpose of our analysis and modeling, we are going to model them as two bulk capacitances. Let us add this parasitic capacitance and see how that is going to affect the EMI and EMC issues in the circuit. In particular, we are going to see how it gives rise to common mode issues. First, we add the parasitic interwinding capacitances and the noise source that we have, as we have already discussed. Now we will identify the current path. The inductor is a high frequency, has high impedance at high frequency, and therefore is an open circuit. The parasitic capacitors have low impedance and therefore are a short at high frequency. Now note that there is some capacitance between the output negative rail and the input negative rail. This may be due to proximity or coupling through the chassis, etc. Now it can be seen that the high frequency current will now flow through the negative rail of the output and pollute the output rails. So basically this current is going to flow out through these two capacitances and appear here. Any impedance on these traces will give rise to a noise voltage at this node. In some applications, as I mentioned earlier, the output terminal must also be grounded. Now let's see what will happen in case the output terminal needs to be grounded on this side. As before, we first draw the circuit diagram. We substitute and add in the parasitic components, in this case the noise voltage, the interwinding capacitances, which we have modeled as bulk capacitances as I mentioned earlier, and parasitic capacitances between the line and neutral wires and the earth conductor. Now we know that the inductor is an open at high frequency, which is what is shown here, and the capacitances are near shorts, and you can see that this large capacitance will present a near short at high frequency. Now let's trace the high frequency current path, which will show us common mode currents. So you can see that this high frequency current from this noise source is going to flow equally through both these parasitic capacitances, and is going to flow out through the line and back into back to the source. So we can see that this is going to give rise to common mode issues. So what is the solution to eliminate this common mode problem? Can we take inspiration from the solution that we used for the heatsink? The answer is yes, we can. We need to add a shield conductor or a strap between the two windings as shown here. This will work in the same way as the heatsink shield, but we have to be a little careful in this case because the shield must not form a complete turn. If it forms a complete turn, then it will form a shorted winding, and we'll end up shorting the transformer or the flyback inductor, and we don't want this. So we have to be careful that the shield does not form a complete turn. The equivalent circuit is now shown here below, and we can see that what has happened is that the parasitic capacitance between the primary and secondary windings has now been split by adding this conductor in the middle. Now the question is, where should we connect this shield in order to eliminate the common mode problem? So let's see that. Now we need to connect this shield to the non-switching end of the primary winding, and I'll explain why. We should basically connect this to the source of the FET, because that's how we can short out the noise source. But if we want to connect this directly to the source terminal of the FET, it may require a large or a long wire, and that may just cause more radiated emission. Instead of that, we know that at high frequency, one of the terminals, that is this terminal, is shorted to the ground anyway. That's because the bulk capacitance, the DC capacitance, is a short at high frequency, and so we can use a relatively short piece of wire and connect the shield conductor to this terminal here. As an exercise, you should think about what will happen if we connect the shield to the other terminal. So if we take the shield and connect it here, which is the drain of the MOSFET. Now, if we connect the secondary side of the high frequency transformer to some switching circuit, then it is possible that the secondary side will have some noise voltage as well, and the shield can cause some of that noise to come from the secondary back to the primary. So what is the solution in such a case? We add two shields, and one of them will be connected to the non-switching end of the primary, and the other one will be connected to the non-switching end of the secondary side. This brings us to the end of this section. Just to recap, we saw a number of real circuits. We looked at the EMI issues in each of those and the solutions for each problem. You should now be able to look at any circuit and able to anticipate and address the EMI issues that may come about. And the next video is the third and last video in the series and contains some example problems and solutions to the same.